This video consists of footage of the build of my Endmill grinding attachment. This tool is more capable and easier to use than the drill grinding jig and Endmill grinding attachment I built some years ago. I can grind drills from 1 to 16 mm, extra long drills, for faceted drills, Endmill end and flutes, D-bits etc. It is used in conjunction with a grinding rest on my surface grinder. The spindle housing body is turned and bored. Here I am turning the spindle shaft outside diameter. The size is critical as it must slide freely in the spindle housing without it being loose nor binding. I machined the spindle housing first as I was short on that type of material, but had plenty of material for the spindle shaft. The fit is what I wanted, glory to the machining gods. Here I am cutting an M32 by 1.5 mm thread for the ER25 collet nut. Unfortunately, I ran out of lead screw and could not use the thread dial indicator. I have another method, but since the material is quite hard, I decided to go manual. For such purposes I fitted the spindle pulley with a handle to crank the lathe by hand. The threading tool lifts up to clear the workpiece. Some elbow grease, but it gets the job done. The nut fits perfectly. Now to bore the taper. When the compound is set at 8 degrees and moved by 20 mm, an indicator set perpendicular to the direction of movement would show a deflection of 20-10-8 or 2.81 mm. To bore the taper, the compound is set at 8 degrees using its protractor. The dial indicator held in the tool post is held square to the compound. The compound dial and indicator are zeroed. And the compound moved by 20 mm. If set correctly, the dial should read 2.81 mm. If not, the compound angle is adjusted and the process repeated till it does. The spindle is supported with a steady rest. Drilling is done at low RPM as the material is hard. The spindle is then bored through. Finally, the taper is bored. The collet should not go all the way in the taper. An end mill is held in the collet and the runout checked. The fit between the spindle housing and the spindle shaft is perfect. These are the raw parts for the cradle, which will be assembled like so. The two vertical blocks are tack welded so they can be machined together. The rough cut sides are milled to size using a small fly cutter. A flat is cut on part of one of the sides to act as a reference for an edge finder. The two previously machined surfaces are ground. The workpiece is flipped by 90 degrees and these sides are also ground. Here I am using my DIY edge finder on the mill jaws and reference surface I milled. Using the DRO, I shall locate the position of two holes which shall be drilled and tapped. The screws holding the spindle to the base shall pass through these holes. First I drill through with a 5 mm drill. I then drill partway with a 6 mm drill, then tap M6. The workpiece is flipped 90 degrees. The edge finder is again used to locate reference surfaces. Two 10 mm holes shall be drilled and reamed. They shall hold two guide rods. A 9.8 mm drill is used to drill through the workpiece. After drilling, a 10 mm H7 reamer is used to bring the hole to final dimension. The welded sides shall be milled to separate the two components. The raw surfaces of the two vertical members of the cradle are ground. The two vertical members of the cradle in position. Next I am making the base part of the cradle. After truing the edges, I need to drill 3 holes. 2 shall house the screws holding the spindle to the base. The third shall be used as a pivot when grinding end mill flutes. Here I am using the edge finder to set the DRO. Holes are located 5 mm from the edge. The distance between the two holes is recorded as this separation needs to be replicated on the spindle housing. First I use a center drill followed by a 6 mm drill. The holes are then counterbored using an 8 mm slot drill. The cap screws shall pass through the vertical support and threaded into the spindle housing. The base is then ground flat. The surface grinder I built has been a game changer, as the fit between parts feels so good. It is worth that extra work. After grinding one side, the part is flipped over to grind the other side. The magnetic chuck is so convenient. Previously, I had to hold parts with low-profile clamps, which was a real pain in the neck. And the part is ready. That finish is really beautiful, and most important, it's perfectly flat. I need to make a cut that mimics the curvature of the spindle housing. This will serve to hold the spindle housing securely. I fitted the dial indicator with a flat tip I made. I shall then zero the dial indicator on the outside diameter of the spindle housing. This shall then allow me to set a boring head to describe the diameter of the housing. I built this boring head some 18 years ago. The tip of the cutter is in contact with the hardened flat tip of the dial indicator. The boring head shall be adjusted till the dial indicator reading equals that, when it was set on the spindle housing. Now I need to set the cradle at the correct height. The holes I drilled in the base need to be on center. I shall use the height gauge to do so. First I set it on the spindle housing and note the reading. The centers of the spindle housing and the base need to be aligned. I need to account for the difference in dimensions between the spindle housing and the base. I shall then correct the height gauge setting. The cradle is bolted to the tool post. It is raised and aligned using two jacks so that the top side is in contact with the height gauge. The jacks shall also prevent the tool from moving the workpiece. The two round bars ensure that the two vertical parts of the cradle are parallel. I then double check with a scribe mark I made, which is aligned with the center of the part. The cradle is then aligned by loosening the tool post and setting it against a bar held in the chuck. And here we go. After reaching the required depth, the spindle housing fit is checked. I'd say it fits perfectly. Here's a better view of how the cradle nestles the spindle housing. The thread in the vertical members used to hold the cradle during the boring operation is removed. The screws need to pass clean through. Next I need to drill and tap 2 holes matching those on the cradle. I use the edge finder to set the DRO. The spindle housing is held in a vise and the edge finder is used to set the X-axis DRO. Holes are drilled 4.8 mm and tapped M6 for 100% thread engagement. I used the DRO to move the distance between the centers of the 2 holes. The second hole is also drilled and tapped. The holes were then deburred. A brake cylinder hone is used to remove any remnants of burrs inside the bore. Finally, the cradle and the spindle housing can be assembled. The spindle shaft is inserted in the housing. Now on to the next part. This piece of scrap will become the protractor. The excess material is cut off. The boss will fit like so. Holes should be at least 8 mm for plug welding, but the collar is 6 mm wide. So I tapered the 6 mm holes with a center drill. Here's the assembly, welded up. The discoloration indicates good penetration. The assembly is held by the collar and the outside diameter is turned. Almost done, it needs another cut. I then face the part. Here is where the angular divisions will be inscribed. I then bore out the remaining crud. I should be on size. Let's try how it fits on the spindle shaft. To inscribe the graduations, I mounted the dividing attachment kit to the lathe backplate. It serves to couple the lathe spindle to a dividing head. This is the dividing head I built, well apart from the plates. It can be fitted to the various indexing devices I built, including to this project. The dividing head worm assembly can be adjusted to accommodate various sized gears. This increases the combination of divisions. Using a 60-tooth worm gear to obtain 360 divisions, the 18-hole plate is used. The handle is advanced by 3 holes for each graduation. The lathe spindle is rotated by 1 degree, as seen on the graduated chuck backing plate. This is the cross-slide stop. It shall be used to make the indexing marks of equal length. The widest spacer shall be used for the smallest tick marks representing 1 degree intervals, a thinner one for the middle marking and no spacer for the tenths. The chuck is indexed by 1 degree. The cutter is brought in contact with the face and moved outwards to inscribe the mark. Moving inwards would result in a burr at the end of each mark. Rinse and repeat for 360 times. A spacer is used to limit the cross-slide travel to inscribe a 1 degree mark. The carriage stop ensures marks are of equal depth and width. After a couple of hours, here's how the protractor looks like. Now to stamp the numbers. I need to face the opposite side of the dial, purely for cosmetic reasons. I use grease to stick spacers to hold the dial using the outside jaws. This dial marking setup is very ad hoc. The number stamping jig is not. This version is for 2 digits. The center line is aligned with the inscribed line. For single digits, a spacer is inserted on either side of the number stamp. And the stamp is given a good whack with a hammer. Here I am stamping a double digit. First, the inscribed mark is aligned with that on the jig. The stamp is placed to one side and a spacer used to fill the gap. The procedure is reversed for the other digit. And the protractor is done. I need to drill and tap 2 holes in the spindle housing and mill a flat where the protractor index mark will be held. This is the hole for the spindle locking screw. The dial indicator is zeroed on the outside diameter of the protractor. I need to machine the curvature of the protractor on a flat piece of stock. This part shall be screwed to the spindle housing and shall bear the fixed mark. Using the dial indicator, the boring head shall be set to describe a diameter equal to that of the protractor. The stock is aligned. And the cut matches the protractor OD. The part is ground for a nice finish. This piece of angle shall become the bracket holding the curved piece on the spindle housing. I am removing the splatter shielding after I welded the curved part to the bracket. The G-clamp held it in alignment with the protractor, whilst the parallel clamp held both part together. It is shaping quite nicely. The weld is milled flat. I am using a spring-loaded scriber to inscribe the fixed mark. Here is the completed bracket. Maybe someday I'll mark it with a vernier scale. Brass thumb screws would not be secure enough, so I opted for cap screws with a brass tip. The threaded end is faced and drilled for a brass insert. Here I am making one of the travel stops. I could not find stock of the required dimensions, so I made it out of a ball joint housing which was close enough. After cutting the excess material, I drilled and tapped it on the mill for the retaining screw. Here is the finished product, the excess material and a ball joint housing. The screw is temporary and will be replaced with one made from soft metal. Here I am testing for axial movement. The dial indicator shows less than 0.005 millimeters, which is acceptable. Any inaccuracy in the protractor or stop would result in a camming action moving the spindle in and out. Not something you want when grinding a cutter. The two 10 mm holes in one of the vertical supports of the spindle housing are cross-drilled and tapped. These are for two brass scrub screws used to secure rods sliding through the 10 mm holes. Here I am making 2 brass screws out of some scrap material. I do not have much to work with, but the automatic carriage feed stop comes in handy when doing multiple cuts. The die holder is kept square to the workpiece by this spring-loaded die pusher I made. Here is how they come together. One of the rods will prevent spindle rotation, whilst the other will be used when grinding Endmill flutes. A 32 mm hole in a 10 mm piece of flat stock needs to be bored. The bulk is removed with a hole saw before boring. This is how it will fit. The rotational stop is drilled and tapped for a grub screw. The holes in the spindle housing need to be replicated exactly in the rotational stop. A center drill is pressed into a piece of rod which locates the hole exactly. This hole is then widened and finally reamed to size. This is my take on the float lock vise. The drill centers on the center drill hole and then the vise is locked in position. The stop is then ground, simply for aesthetical reasons. As its name implies, the rotational stop prevents the spin indexer from turning. In conjunction with the guide rod, it only allows axial movement. This is necessary when grinding the end face of an end mill. The spin indexer handle is finished with a shear tool. This tool removes a tiny amount of material and produces a superb finish. This version is made from a used carbide insert. The handle attaches to the rotational stop like so. Now I'm making the locking screw. The puck from the rotational stop will serve to make the knob. threaded rod, with a brass insert, is pressed in the knob and then welded. The knob is then turned and faced. The screw is held in a hex collet block. The collet block is indexed and held in the same position by resting against the vise stop. Plunge milling produces 6 scallops. The base is drilled then counterbored using an end mill for the pivot screw. Holes for clamps, stops and locking screws are drilled and tapped. The base is then ground. A shoulder screw is turned from an 8.8 bolt. The base of the spindle housing is slotted by chain drilling and filing. This allows the spindle to pivot.